Hello everyone, welcome to the 10th module of this course on microsensors and nanosensors. And this module is all about displacement sensors and accelerometers. This is our first lecture, and initially first lecture as well as in second lecture we will talk about mostly on displacement sensors, and in the subsequent lectures we will cover the accelerometers. Both are very important in the perspective of practical applications. So all these kind of sensor, both displacement sensors and accelerometers, we will talk in the context of microsensors and nanosensors, or mostly the miniaturized sensors. So let us first talk about position and displacement sensors. So what is a position? That is important, and first we have to understand the position and displacement, then only we can talk about development of sensors to detect these things. So position refers to the identification of an object's coordinate. Okay, so this coordinate can be a linear or it can be angular. Okay, so these positions can be either linear or angular, which of course has to relative to a chosen reference point, or there should be a reference frame whose reference we are taking to find these coordinates. Okay, so now once we understand this position, we should understand the displacement, which refers to the change in the position of an object. Of course, in this change we are not only covering the distance from that coordinate, but we are also talking about its direction of change. Okay, so this displacement refers to the change in the position of the object, which involves movement over a specific distance or through a certain angle with the known direction. Okay, so displacement, since we are discussing a course on sensors, so we have to actually find this displacement. So only understanding this physical meaning will not help. Okay, so to find the displacement, position can be compared by its current position. So if I have a known object's current position, I can compare it to the previous position where it was located earlier. Okay, so these coordinates can be compared and the displacement can be found with the affirmation of the direction. Okay, so if you notice, we are not taking any external reference point. What we are taking is, we are taking the current position of the object as well as the previous position of the object itself. We are not taking any help of any external reference point. Okay, say for example, I can also talk about say I have a micro object. Okay, and say this cantilever is moving in certain direction, and I can say that this cantilever's position is changing. Say if it is angular movement. Okay, so earlier position, this was the first position and this is the current position. I can take this movement of this cantilever with respect to this micro object, which has to be in the vicinity of this micro cantilever. Okay, so I can compare its position. So this is the external reference point I am talking about. I can talk about the movement of this cantilever with respect to this point, or as well as I can talk about its current position with respect to its original position or the previous position. Okay, so if I know the previous position, I do not require any external point. Okay, so the displacement is determined by comparing object's current position with its previous position rather than to any external point. Okay, and this kind of position or displacement sensors are very relevant at various applications, including robotics, where joint feedback is required for precision control. Then in automotive, for throttle, pedal, suspension travel, you require this kind of displacement sensors. Okay, for industry automation, it is very much required. Okay, for aerospace, where you require a lot of flight control, there this kind of displacement sensing is required. Okay, and for medical application, there are a number of applications, including prosthetic limbs, where these kind of displacement sensors are required. Okay, so there can be similar to other sensing module that we have seen, these sensors can be based on various transduction technique, including the simplest one, which is potentiometric, which we will see in a while. Okay, So position and displacement sensors can be of various type, including potentiometric, which is the simplest one that we are going to see in a while. Okay. Then these sensors can be based on capacitive principle. Then you have eddy current based sensors, then magnetorestrictive or magnetoresistive devices, then optical devices, ultrasonic devices, Hall effect based sensors. Then you have LVDT and RVDT, which is linear variable differential transformer, as well as rotary variable differential transformers. We will try to cover some of them, but understanding the first one, which is potentiometric, is very much required, particularly to understand the subsequent displacement sensors. So let us try to understand what is potentiometric sensors, potentiometric displacement sensor, and why this is very significant in our discussion of the rest of the topic. Okay. So in a potentiometric device, which is as the name suggests, there is a wire whose length changes when the wiper's position changes, and the wiper, so this is the wiper that I am talking about. It is connected to the object which is moving. Okay. So basically we want to find the displacement of this particular object which is connected through this wire in this potentiometric device or in this resistance. Alright. So this resistance is directly proportional to the length of wire. Wherever this length is there, if this wiper is moving, this length is actually governing the resistance of the wire. So wherever it is connected, I am talking about that particular resistance only. So resistance is directly proportional to the length of the wire. We already know, and we will use that in this kind of configuration. Okay. So by using an object to control the wire's length is important, and that is very similar to a potentiometer. Okay. So by measuring this movement, the displacement can be measured, and this kind of sensor is a active sensor. So you need a certain kind of biasing. Okay. So this moving object is mechanically linked to a potentiometer wiper like this. Okay. And its motion results in a change in the resistance. So if it is going downward, means it is probed over here, and I am taking consideration into only this much wire's length. Okay. And I know that R is equal to rho L by A, or this R is directly proportional to length. Okay. I am governing this length. Okay. So this moving object is mechanically linked to this potentiometer wiper, and its motion result in a change in the resistance. Okay. In most practical circuits, this resistance is typically measured not directly, but basically indirectly. Okay. And this indirect measurement is basically by observing the voltage drop across the wiper or the probe. Okay. So the voltage at the wiper of a linear potentiometer is directly proportional to the displacement D. So this is the displacement. Okay. This is the displacement I am talking about, and this voltage that has been dropped across this is equal to the total supply, okay, the voltage across the pot into this small d by capital D, where the capital D is the full scale displacement which is possible with this kind of device. Alright. Please note that in this simple equation, I have not taken into consideration any error which is arising due to interface circuit or by any other mean. Okay. This kind of equation is written by assuming that the interface circuit do not introduce any significant electrical loading into the device, which is practically not possible. Okay. So if a substantial load is present in the circuit, the linear relationship between the wiper position and the output voltage will be disrupted. So now it will not be linear as we have just now seen. Okay. Further, the output signal depends on the excitation voltage across applied across the sensor. So this voltage E is also present in this equation. So for this equation to hold, okay, the linearity equation to hold, we have to assume that this E is not changing, or this voltage is kept constant. Okay. In any mean, if this E is disrupted or if it is not constant, it will introduce the measurement errors into the device or into the potentiometric system. Okay. Of course, there has been various ways to address this kind of issues, okay, and one of the important way to eliminate these effects is by using ratiometric analog to digital converter within a microcontroller, which this kind of AD converter cancels out the effect of voltage fluctuations, okay. So, a potentiometric sensor function as a ratiometric device, not a individual device. It is basically taking into consideration of the ratio of the lengths. Okay. So, particularly in terms of resistance. Therefore, the resistance of the potentiometer do not affect the output. Okay. Provided that the resistance element is uniform along the entire length, which is practical in most of the cases. Okay. Or in other words, we can say that only the ratio of the resistance is important and not the individual resistances. Okay. So, which means that these devices or this kind of system do not have to do anything with the stability of device, okay, or the stability of the potentiometer itself do not affect the measuring accuracy, because stability can affect the individual resistances. It will have similar effect in both the resistances and they will cancel out each other when we are taking the ratio. Okay. So, it will not affect the measuring accuracy if there is some instability with the system, all right, or instability with the individual resistances or with the potentiometer. Okay. So, in low power applications, high impedance potentiometers are mostly preferred. However, the loading effect must always be taken into account, and the loading effect comes from the interface circuit that we have just talked. Okay. So, mostly you will require a voltage follower circuit for this. So, typically the potentiometer's wiper is electrically isolated from the sensing shaft to avoid any kind of external loading. Okay. So, this is a basic potentiometer sensor, and we will see that although these devices are very simple, there are certain limitations of these kind of sensors. It cannot applied for all kind of application. Although what we have seen just now is a kind of linear potentiometer, okay, where the measurement is a straight line displacement. Okay. But there can be cases where you deal with angular or rotational movement, that kind of for those kind of application you have rotary potentiometer, and you also have another kind of displacement sensor based on potentiometer, which is known as multi-turn potentiometer, which is having high resolution for longer ranges. Okay. So, basically these two potentiometers are very popular, which is linear potentiometer and rotary potentiometer, but then there is third kind of potentiometer exists, which is multi-turn potentiometer, and discussion on multi-turn potentiometer is beyond the scope of this course. Okay. However, if we have basic understanding of a potentiometric displacement sensor, we know that these kind of devices are very simple, be it rotary or be it straight line or a linear displacement sensor. They are very simple, and since only a resistance or battery is involved, although even if you talk about circuitry, there is a inexpensive kind of circuit is involved. So, these devices are basically very inexpensive and they have analog output, so can be easily interpreted. Okay. These devices have high resolution and better linearity, okay, and they work in low speed application very well. Okay. These are certain advantages associated with potentiometric sensors, but then there are certain limitations which are associated with this kind of devices. First and important limitation of these devices are they are contact based devices. Okay. So, wherever you want to I mean the object whose displacement you want to measure has to be in contact. Okay. So, because of that it is subjected to mechanical wear. Okay. They are also susceptible to dirt and contamination because of the wiper and external ambient involved. Okay. Then since there is a mechanical friction also associated, the lifespan of these devices are limited and these are not suitable for high speed dynamic measurement. However, for low speed kind of measurement, these kind of devices are very much suitable. Okay. Therefore, we have to look for other kind of displacement sensors, and in the beyond potentiometric displacement sensors, the other device which is very simple, very similar to this, is a capacitive displacement sensor. Of course, if you talk about MEMS capacitive displacement sensor and others, there are certain complications associated with the fabrication. However, the principle remain very simple. Okay, and this capacitive position sensor operates by either altering the geometry, as we have seen for other kind of devices also, other kind of applications also. They work by operating in either altering the geometry configuration or by detecting change in the capacitance, and all this is based on the formula for the parallel plate capacitor, which is C equal to epsilon A, where A is the area, D is the gap, and this epsilon is the permittivity. Okay, so this can be based by changing the geometry factor. If you remember, we have seen that C is equal to epsilon kappa. This kappa was equal to this was the geometry factor, and this was equal to A by D, right? So we can measure by changing this kappa, okay, or by changing this epsilon, which is the permittivity. Okay, so it can be measured by altering the geometry or by detecting change in the capacitance caused by the nearly conductive or dielectric material. Okay, so this is just one configuration, which is parallel plate kind of configuration. So but they exist in different form factors. Okay, so parallel plate capacitive sensors are mostly suitable for displacement changes. Okay, in straight lines. Okay, then interdistributed capacitive sensors are for mostly applied for lateral motion kind of detection. Okay, then you have cylindrical or coaxial capacitive sensors, which have non-flat geometry, and that kind of application you can think of. Okay, then you have MEMS based capacitive sensor, which are very popular at micro scale displacement measurement. Okay, so however, the principle remain more or less similar. Okay, so when the capacitance changes, this C value changes, it can be simply converted into a variable okay, so these sensors can be configured by various means. It can be configured as a monopolar, where you have only single capacitor associated. You have differential arrangement, where you have two capacitor involved, or it can also be configured in a bridge kind of circuit or in a capacitive bridge. Okay, where you have multiple capacitor, like 4 different capacitors are involved, where 1 or 2 capacitors are changing. Okay, so when using 2 or 4 capacitors, half bridge or full bridge kind of configuration, 1 or 2 of them can be fixed and others can be variable. Okay, and they operate in opposite phase to each other. We will see this configuration with one example, which is very important for micro sensors. Okay, consider this kind of plate arrangement. You have a central plate. Okay, you have a central plate. Okay, then you have top plate and you have a bottom plate. All right, you have a 3 plates arrangement. Okay, at the top plate you are providing a voltage, a sinusoidal voltage of V naught sin omega t magnitude, and the inverse of it, minus V naught sin omega t, you are applying to the bottom electrode or bottom plate. Okay, the central plate remains at 0. Okay, now if you see this 3 plate configuration, the top 2 electrode is making a capacitance C naught, which is at a distance x naught. Okay, from the central plate. Exactly, the second plate is also at a distance of x naught at a equilibrium position, and it is forming a capacitance C2 with the bottom electrode. Okay, now as I have mentioned that upper and lower plates are supplied with a sine wave signal, as in the form of V naught sin omega t. Okay, and they are at 180 degree out of phase with each other. Okay, both the capacitors are nearly equal to each other. Okay, so C1 initially is equal to C2. Okay, therefore the central plate has almost no voltage with respect to ground, and that's why I have mentioned that the voltage at the central plate is 0. Okay. So we can indirectly also say that the charges on capacitor C1 and charges on capacitor C2 will cancel each other. Okay. Now let us assume that the central plate has a movement, okay, and this movement is in the downward direction. All right. So in this 3-plate configuration, if this plate, say this was at this position initially and it moved to this position now, okay, means that from the bottom the distance is decreasing. Okay. So that's why the central plate and or D between the central plate and the bottom electrode is around x naught minus x, where x is the movement of this central plate. Okay. And the D between the top plate and the central plate increases and it becomes x naught plus x. These distance will of course have effect on capacitance C1 and capacitance C2. Okay. So the new capacitance C1 becomes epsilon A by x naught plus x. Please note that there is no change in area involved here. Okay. So C1 becomes epsilon A by x naught plus x, while C2 becomes epsilon A by x naught minus x. Okay. Now because of this, now the central plate's voltage will or the central plate will no longer be at 0 potential. Okay. There is certain potential associated at the central plate. Okay. This voltage is proportional to the displacement of the plate. Okay. And the phase of the signal indicates the direction of the central plate's movement. You know that for displacement, along with the distance of movement, the direction is also required, and this direction is given by the phase of the signal detected. Okay. So it can tell you about the upward movement of the central plate, or it can also tell you about the downward movement of the central plate. Okay. And the amplitude of the output signal is given as V naught into minus x by x naught plus x plus another factor delta C naught by C naught. Okay. So as long as this movement x is very small as compared to the initial positions of x naught from the central plate, the output voltage can be considered as a linear function of the displacement. Okay. Please note that in this equation, this second term delta C naught by C naught is very important, and it represents any initial mismatch in the capacitance, okay, and is the main source of the output offset. Okay. So the offset can also be caused by the fringing effect at the peripheral portion of the plates and by the so called electrostatic forces. Okay. The forces which arises from the attraction and repulsion of electric charges applied to these plates, it can also behave as a spring, because there are certain forces associated with these charges. Okay. And in terms of the capacitance, this instantaneous force can be given as minus half C by x naught plus x into V square. Okay. So this kind of capacitive displacement sensor is very important, where the movement of a central plate, of course, which is tied to an object, the measurement of upward and downward directions are involved. Okay. So that kind of displacement it can detect very easily. Okay. And the same can be implemented using a MEMS device. Okay. So this is a kind of fabrication of a MEMS device or MEMS capacitive displacement sensor. Okay. In this design, two individual plates are created using MEMS technology, and both are of course made up of silicon. Okay. So in this, the plates are micro machined from the silicon itself. Okay. No other material are involved. Okay. So in this configuration, one plate serves for the displacement measurement, while the other acts for or other is important for a reference. Okay, so one plate, this is the reference plate and this is the sensing plate. Okay, so both plates have nearly identical surface areas. However, the measurement plate is supported by 4 flexible suspensions. So these are 4 flexible suspensions, while in the reference plate these suspension, there is no such suspension. Basically they are stiff suspension, okay, or these are not moving. Okay, so the reference plates is basically secured using this rigid suspension or stiff suspension. Okay, so only the movement is because of this sensing plate, and of course this has to be measured with respect to the reference plate. Okay, so this kind of devices are very important for measurement at a micrometer kind of displacement. Okay, so this capacitive sensors have usually very high resolution, and some micron or nanometer kind of resolution is possible. Okay, these devices are non-contact and mostly wear-free operation is possible. Okay, these devices have fast response time and higher bandwidth is associated with the operation. Okay, they are very sensitive to small displacement and they have very high sensitivity. Okay, they require clean and stable ambient for best performance. Particularly this is associated with any dielectric changes with respect to the dust accumulated or water accumulated in between the plates. Okay, so they require a clean and stable ambient for their performance. However, there are certain limitations associated with this kind of devices. Particularly they have limited range. Okay, then they are sensitive to humidity, dust and other contaminants from the ambient. Okay, they require careful shielding to prevent any EMC kind of problem. Okay, they have relatively complex signal processing electronics. Okay, so backend electronics is complicated, particularly if you compare it with the potentiometric kind of devices. Okay, then there is another kind of displacement sensor which is very popular, which is known as eddy current displacement sensors. Okay, so eddy current sensors are mainly employed to measure the displacement and position of electrically conductive targets. Okay, these electrically conductive targets may not be magnetic material necessarily. Okay, so they can be used for both ferromagnetic and non-ferromagnetic materials. Okay, and their high resistance to oil, dirt, dust, moisture and magnetic interference makes it suitable for harsh ambient kind of applications. That is not possible with the potentiometric and capacitive devices. Okay, so they are very much ideal for being used in harsh industrial conditions. Okay, so the eddy current method operates using high frequency magnetic fields which are generated basically by passing a high frequency alternating current through a coil within the sensor's head. Okay, so when a metallic target enters this magnetic field, electromagnetic induction causes the magnetic flux to flow across its surface. Okay, this electromagnetic induction generates eddy current which is perpendicular to its surface. Okay, so these eddy currents alter the sensor's impedance and it detects this change. I mean, the sensors work on measurement of these changes in impedance, or these changes is indirectly proportional to the measurement of distance or displacement of the target. Okay, so eddy currents can arise in two situations. The first situation is when a conductor is subjected to a varying magnetic field caused by relative motion between the conductor and magnetic field sources. The second situation can be the intensity of magnetic field itself changes over time. So in both the cases eddy current you can get. Okay, so these effects basically generates a circular flowing electron within the conductor, particularly at the surface, which is known as eddy currents. Okay, now according to Lenge's law, these circulating currents produced at the surface, okay, they induce some magnetic fields which opposes the change in the original magnetic field. Okay, so this result in repulsive or drag forces between the conductor and the magnets. Okay, So the stronger the applied magnetic field, or the greater the electric conductivity of the conductor, or I can also say the faster the field of the conductor is exposed to change, the current levels changes at higher pace, okay, and it opposes this field at high rate, and based on this the impedance changes is at faster rate, and these devices therefore are very fast. Okay. So detect the proximity of non-magnetic yet conductive materials, eddy current effects are utilized. Okay. Mostly these sensors exist in dual coil kind of configuration, as we have also seen for capacitive devices. You do not have only one plate, you have reference plate as well as there is one sensing plate. So one is moving and another is rigid. Similar kind of configuration is possible in eddy current displacement sensor, where they appear as a dual coil kind of configuration. In this kind of configuration, one coil serve as a reference, or we call it reference coil, while the other acts as a sensing coil. Okay. So this sensing coil basically senses the magnetic current induced in the conductive object. Okay. So if the conductive object is here, the sensing coil is the first which will face the change in the magnetic current. Okay. So the eddy currents basically generates a magnetic field when it comes into vicinity, and this of course eddy current, this magnetic field which is generated by the eddy current opposes the field of the sensing coil. Okay. This creates an imbalance relative to the reference coil. Okay. The closer is this conductive object to the coil, the greater is the change in the magnetic impedance, and the depth at which these eddy currents are generated within the object is mostly determined by the skin effect delta, which is given as this delta is equal to 1 by root pi f mu sigma, where mu is the magnetic permeability, f is the frequency, and sigma is the target conductivity. Okay. So for effective operation, the object's thickness should exceed the depth at which these eddy currents are generated, and therefore this eddy current sensors are basically not suitable for detecting thin metallized films or foil kind of materials. Okay. In general, the relationship between the coil impedance and the distance of the object x is nonlinear and influenced by temperature as well. So eddy current sensors typically operate between, not exactly, but in between 50 kilohertz to around 10 megahertz. Okay. From the fabrication point of view, they exist in two configuration. One is shielded and another is unshielded. There is slight difference between them, as you can see from the figure also. Okay. This one is the shielded eddy current displacement sensor, and this is unshielded eddy current displacement sensor. In the shielded version, this version, a metal guard, this metal guard surrounds the ferrite core and the coil assembly. Okay. This material, the shield concentrates and directs the electromagnetic field towards the front of the sensor where this conducting object was placed. Okay. So this enables the sensor to be mounted or even embedded within a metal structure without affecting its detection range. Please note that it can be embedded within a metal structure. Okay. However, the unshielded sensor can detect object from both its sides and front, which is not possible in the case of a shielded one. Okay. Consequently, it typically has a slightly greater detection range than a shielded sensor of the same dia. Okay. However, for proper operation, unshielded sensor require a non-metallic surrounding environment, and means that it cannot be embedded into metals. Okay. That is one of the biggest disadvantages of unshielded eddy current displacement sensor. Okay. So you always require a non-metallic surrounding environment. Okay. And that is why most of these sensors, eddy current displacement sensors, are based on this shielded effect. Okay. So there are various advantages associated with this eddy current displacement sensors. The first and foremost advantage is they are non-contact kind of devices, therefore have wear free operation. Okay, they are insensitive to dust, oil or other contaminants. Okay, they operate in high temperature and vacuum kind of ambient, and they have high precision and fast response time as compared to other sensors where the plate will move, then dielectric will change, and those kind of things is not involved. Here you have direct induction of magnetic field, and because of that there is change in current, and that's what we measure. Okay, so this kind of devices works well with conductive target in motion. Okay, for non-conductive it is not possible. Okay, so that is basically the limitation. So only this kind of devices only work with the conductive targets, particularly non-ferrous or ferrous kind of metals. Okay, the measurement range is relatively shorter as compared to the other devices. Okay, they are sensitive to temperature and materials variation. Okay, and they require complex signal conditioning circuit. So signal conditioning circuit associated with this kind of device is very complex, and of course you do not need that kind of complication, particularly for signal conditioning. Okay, and then the biggest disadvantage of this kind of device is they require calibration frequently, and this calibration is material specific. So if you are using material X, you may have to change the calibration to a method Y. Okay, so that is the biggest disadvantage, and that's why there are other displacement sensors or position sensors also been reported. So what we will do is in our second lecture we will talk about the rest of the displacement sensors before we actually move towards the accelerometers. Thank you.